Vertex. Right. Now here are some nice properties of tournaments. Tournament has a cycle. Again, this was the other. The cycle isn't only if it has a small director, which is a triangle, the smallest possible. Which means equality, a tournament has no cycle if and only if it has no triangles. And again, we saw this the other day. If you have a tournament which is a cyclic, which has no triangles, no cycles, you can list out its vertices in an order, say V1 to Vn, such that every arc, every directed edge in the tournament goes from left to right, from vertex before to vertex after. And this we can do exactly now. So here is on the left is a tournament which is a cyclic, more directed cycle. And on the right side, you can see I have relabeled the vertices in such a way that you can see. The vertices are V1, etc., V5, and all edges go from Vi to Vj, I. Right. A feedback vertex set of a tournament is a set of vertices such that if you delete those, then there won't be any more cycles left, directed cycles left in the vertex. So on the left is the original tournament that we saw, and the vertices marked with red they form a feedback vertex set, because once I delete those, I get this tournament which is on the right side, and it has no directed triangles, there are directed cycles. Right. And the problem that we are looking at is called weighted feedback vertex set in tournament. So the input is a tournament with non-negative integral weights on the vertices, and the task is to find a feedback vertex set, which is a smaller set of vertices whose deletion will leave a tournament without any cycles. So find such a set with the total weight being the smallest. So you find a small set, a set of vertices. If you delete them, there are no more cycles left, and you want to find such a set of vertices such that the sum of the weights on them is the smallest. So that's it. Now this is NP hard even if you don't have weights on the vertices, or equality if all weights are 1. And we can approximate this to constant factors in polynomial type. So if you don't have any weight on the vertices, or if all vertices have weight 1, then there's an easy or simple 3-factor. Can you say how? So we observe that there's a cycle in the tournament if and only if there's a triangle, which means to kill all cycles, you have to kill all triangles. And if you pick a triangle, there are 3 vertices in it. You have to pick at least one of them in your feedback vertex set. If you pick all 3, you are not doing much worse than 3 times the best. So the simple 3-factor experiment consists of find a triangle, that triangle, delete all its vertices. So you have to delete at least one, you delete at most 3. Exactly. So that's a simple 3-factor. Now, when you add weights to the vertices, this trick will not work anymore. Right? So, for instance, if you had just one triangle, the whole graph was just one triangle with weights, let's say 1, 2, and 3. This was an entire graph, and the weights were 1, 2, and 3. The lightest weight feedback vertex set has weight 1, but if we take so if this was the entire graph, the smallest weight feedback vertex set had weight just 1. But if you try this trick of taking all 3 vertices, you will end up with a weight 6. And this we can make as bad as we want by taking the weights. So the simple trick doesn't work for if you have weights on the vertices, but using a slightly more involved idea called the local ratio technique, we can sort of leave this kind of an approach to get 3 approaches. Right. And then, so this is, once you know the local ratio technique, this is possible. Then that was the case for a long time, and then in 2000, Sai et al. Used again the same local ratio technique to get a 2.5 approximation. And then most recently, in 2016, NISER et al. Found an even better approximation, 7/3, which used the local ratio technique plus something called iterative running. So we don't need to know what iterative running is. but we'll see a bit about the locking ratio there. Okay. We also know that it's unlikely that we find a polynomial time approximation with a factor strictly less than 2, assuming the unity is contained. So there is a simple reduction of Vertex curve is here. Okay. So what we show is that we can in fact get a 2-factor approximation. So this is kind of the best possible in randomized polynomial time. So what does our algorithm do? Given the input which has n vertices, it runs in some n to the c time. It will output a feedback Vertex set, and this feedback Vertex set will be a 2 approximation solution with probability half. And this can be randomized easily to run in something like n to the order logging time. Okay. So the algorithm has 3 main ingredients. The first is the locking ratio technique, and then randomization, and divider. Yeah, we'll see all these things. Okay, so let's look at this famous locking ratio technique. Right. So we have this problem. We first get 3 approximations for the weighted tournament feedback Vertex using locking ratio. So the input is a tournament and with the weight function of the vertices, and you want to find the smallest weighted feedback Vertex. Right. So it's enough to kill all that angles. Right? So here is the idea. So recall that in the simple unweighted case, we went and looked for a triangle, then picked all 3. Here also we go and look for a triangle, but we look for a triangle where all 3 weights are positive. We are all 0 weights also. Now what we do is we do this weird thing of subtracting the weight of the least weight vertex from all the 3 weights. So if you happen to find, so let's say this triangle was there in the graph, the step that you do will take the same graph, but this triangle, these weights will become 0, 1, and 2. So you go and find a triangle where all 3 vertex weights are positive, and reduce the least of these weights from all 3 weights. Keep doing this till you cannot find any more triangles with positive weights, and then you output the set of all 0 degree, 0 weight that you found in the end as the solution. So the algorithm is simple. Go and look for a triangle with all 3 weights, the vertex weights positive. Reduce these weights in this weird manner. At some point, you will not find any more triangles where all 3 weights are positive. In that case, look for those vertices which have 0 weights now. So just return all of them as your solution. And the claim is that doing this is actually like good. That will actually give you a 3 approximate solution. So notice that if we had one weighted case where every vertex are around the weight of 1, then doing this would give us a 3 approximate solution. Right? Because that's what we did previously, right? So we went and found a triangle, all weights are 1. We picked all the solution. Here we would set all those weights to 0 because all weights are 1. So in the end, the vertices whose weights you set to 0, those are what we would return in the simple case. So the same things, the same set we would return here also. So this is somehow a generalization of the simple pick all 3 vertices case. Yeah. And this does the job also in the weighted case, even if there are weights involved. Just doing this and returning all the 0 weight vertices would give you a clear problem. Let's see one. Okay. The first claim is that if S was a set of vertices whose weights ended up being 0, those guys form a feedback vertex set of the tournament. Why is that? Sorry? Yeah, so in the end, every triangle had at least one vertex of weight 0, otherwise it would have done something. Yes? So the set as a 0 weight vertex, in fact, form a feedback vertex set of the entire tournament. Because you do this till you find, like, sort of make every triangle have at least one 0 vertex. 0. That's good. part is that this set S has total weight at most thrice the weight of the best or the least weight feedback vertex. Let's see why. Okay. Okay, so here's what we do. Yeah. So let the set S is a set of vertices which ended up having 0 weight at the end. And the claim is that the total weight of these guys in the beginning is not more than the total weight that we reduced from all vertices through all this process. Yeah, because the set S is a subset of the set of vertices whose weights we reduced. Therefore, the total weight that this set S traveled with is not more than the weight we reduced in total during the entire process. Is that confused? Yes or no? It's confusing. So the set S, the claim is the following, right? So you did some adjustments of weights. In the end, there was a set of 0 weight vertices. The claim is that if you looked at the weight of S, weight of all things in S when they start around, this is at most the total weight that you reduced by the during the entire process. And this is true because if you look at the set of all vertices whose weights were reduced during the process, this set S forms a subset of all vertices because all the guys start out with weight 0 or more. In the end, these are the vertices which will now have 0 weight. So the total weight that you reduce. These guys form a subset of all vertices whose weight you ever reduce. Any. Okay. So now, so if you reduce the total weight of 3R in one round, so recall that in one round you find a triangle, one vertex of some weight, let's say R, or smallest weight, and reduce this weight R from all 3 guys. So in each round you reduce a weight of 3R for some R. So if you did that, look at any one round, then you reduce this weight by 3 times R. Then the weight of an optimal feedback vertex reduced by at least R. What I mean is that you had a tournament with some weights, you found a triangle, and you reduce its weights in a certain way. So this guy had a feedback vertex of some weight, optimum feedback vertex. Yeah. So this guy had an optimum FPS. Yeah, the weight of your optimum FPS. And this guy has also some other weight of an optimum FPS. So what it says is that the drop in this from here to here is at least 1/3 of the total weight that we reduce. So here is the argument. Look at one triangle XYZ that we modified. So X, Y, Z. And let's say the weight of X was the smallest. Yeah. So this was some R plus something, P, this was some R plus Q. So what we did was we made all these weights to these factors. Yeah, 0, P and Q. Yeah. So look at an optimal FGS of this tournament before we did the reduction. That optimal feedback vertex had to be at least one of these 3 vertices in it. Now, the same set is a feedback vertex of the new graphs. And the weight of this feedback vertex went down by at least R, because you pick at least one of these guys in your original feedback vertex. The same set is a feedback vertex here, so the weight of that particular feedback vertex set reduced by at least half. So the optimum weight of the feedback vertex set also reduced by at least half. Okay. Right. So now, suppose over all rounds we reduce the total weight of 3 times Q. Then the total reduction in the weight of an optimum FPS is at least Q. We just with adding up all this production. Okay. So now we are. One more thing is that the weight of an optimum feedback vertex set of the last final instance is just 0, right? Because when you end, every triangle has at least one vertex of 0 weight. Just picking all of these guys would keep all triangles. So this means us that the weight of an optimum feedback vertex set of the original graph is at least Q. Right? We started out with some unknown feedback vertex weight. You ended up with the weight of 0. And the reduction was at least, so the weight of an original optimum feedback vertex set was at least Q. And now we have what we want. So weight of the set that we pick, at most 3 times Q, which is at most 3 times the weight of the best feedback vertex set of the original instance. So this thing works. If you find a triangle, reduce the weights in this particular way, and then just return all the 0 weight vertices, it just works. Because okay. Alright. So that was the 3 approximations for weighted closeness, weighted feedback vertex weighted closeness. And to get at the 5x2 approximation, what Sci did was they found 2 graphs, each on 5 vertices. So the first graph is actually a collection of a few graphs because I did not draw some of these arms. They found 2 graphs such that any feedback vertex set must pick at least 2 of these 5 vertices from each graph. This is easy to verify. And the interesting thing that they do is that if none of these graphs is present in the tournament, then you can find an optimum feedback vertex set in polynomial time in those kinds of tournaments. So there are these guys, 2 guys which are, if they are there, then you know that you have to pick at least 2 out of each of these 5 guys. If they are not there, you can find a best optimum in polynomial. So now the local ratio technique, we have to pick 2 out of 5. So the local ratio technique now gives you a 5x2 approximation. Alright. Any weighted case, even this case. You are in the weighted case. So this gives you the 5x2 approximation.
So algorithm will be 5 one of these structures, find the minimum one, reduce everybody
by that weight and repeat. And if you cannot find this fall. So that was 3 goes to 5x2. Right? So how do I go from 5x2 to 2? So one way could be to find something like what side goes. Right? Maybe find some set of, let's say, 10 vertex graphs such that every feedback vertex has to pick at least 5 of them. And if these 10 vertex graphs are not present, then you can solve polynomial time exercise. But then that's hard work, and why should such things even exist? So what we do instead is we apply the local ratio study with some extra support. So we find a vertex, a graph on 2 vertices, such that any solution must pick at least one of these 2 vertices, and then we apply the local ratio technique. Yeah. So this is what we do. Yeah. Let's see. And the steroids that we use are you take local ratio technique and sort of lift it a bit, then randomization and just do what I do. And these are not our own stuff. All these 3 are the second and third are really well known, and the first one is known in geometry circles at least, people in approximate circles. Okay, let's see what these 3 ideas are. So our generalized local ratio technique applies when there is an optimum solution. So when there is a minimum weight feedback vertex set with a lot of vertices. So suppose in our tournament T with n vertices, suppose there is an optimum solution. Optimal means smallest weight, which contains at least 2/3 of the the vertices of the smallest weight. So then the total weight of these n by 6 guys is not large compared to the weight of the optimum solution, which is 1/4. Okay. Now this implies that if you want to get a 5/4 approximation, you can just pick all of these n smallest weight guys in the solution, find an optimum solution for the remaining instance, and add these together. Because these guys don't harm. The weights of these guys are so small together that they don't harm the optimum by now. But the hard part is, of course, how do you find this optimum for the remaining one, which is like we don't have 5/4. Okay, but it turns out that this, if we fudge this a bit, then it works. So here's what we do to get a 2 approximation. We find this at L of what is this? N by 6 what is all this? Weight of this stuff. No, the size. This is the cardinal. So to get a 2 approximation, since we cannot find an optimum because it's again a hard problem, we find the set of smallest weight vertices. We take them into oscillation. Now we modify the weights of the rest of the guys similar to the way we did for the local machine. So there are this set of L things of the smallest weight. Find the weight of the largest weight guy among them. Delete that weight from the rest of those guys. So we would end up picking all of these n by 6 guys of smallest weight, fine. And for the rest of them, we will reduce each of their weights by the maximum of weights of these L guys. And then we find a 2 approximate solution for this instance. You took these guys, reduce their weights, of the remaining guys, so that's a new weight that we find. You find a 2 approximate solution. You don't want to find that next action. Find 2 approximate solution, take the union, and this will give you a 2 approximate solution for the original instance. So this is sort of like what we had for the simple calculation.
So approximation of the thing is recursive.
Yeah, because we find the source code. Right? Let's see why this, why this is. So here's what we do. Find the n by 6 vertices of the smallest weight. Let max L be the weight of the heaviest of these guys. Define a weight function on the rest of it, V minus L, by taking whatever their weights were and reducing this max L. And the reduced instance we have is remove L, change these weights by these amounts. That's it. And let's say R approx is a 2 approximate solution for this reduced instance. The claim is that if you take all of R approx, add all stuff, we get a 2 approximate solution for the original instance. And that's a claim. And why is this true? The intuition is the following. So remember that S star, an optimum solution, was like 2n by 3 vertices. So S star minus L is very large compared to just L in terms of numbers of the cardinality. Also, S star minus L is a solution, not necessarily optimum, of the reduced instance. Yeah. Because when you delete stuff, feedback what I said, but the remaining part is still a real. So S star minus L is a solution to the reduced instance. Now, we reduce the weight of vertices in this main of so many vertices by this max L. So max L was the weight of the heaviest guy in this setup. And then there is a huge set S star minus L. We reduce the weight of all those guys by this max L. So this causes a very large drop in the optimum value for the reduced instance R. Lots of guys, each of guys weight we reduced by a certain amount, but that was the max weight of the guys that we removed. So the reduction of weight, since we reduce the weights lots of vertices by this max L, this caused a large drop in the optimum for the reduced instance. And this drop is enough to accommodate putting all of L back into a 2 approximate. So this is just the intuition. You took a certain number of guys of small weight, and then you reduce the weight of a lot of guys by a certain amount. So there is a huge drop in the optimum in the remaining, and that drop is enough to accommodate a 2 approximate solution. But even if you just add all of L back without enough to sort of preserve the two approach. So I will keep the proof. It's not. It just puts what I said into the formula. I'll just skip this proof. So this is what we have. Then if it so happens that there is an optimal solution with a lot of vertices, then this is what we do. Sort of pick the lightest vertices, a few, lot of them, not many, into a solution and reverse. Okay. So now, so this is this one. L and you ignore proper solution and content. So now what if there is no optimal solution which has lots of vertices? So now we apply the second step, right, which is randomization. Now suppose there is no optimum with 2n by 3 vertices. So every optimum solution is less than 2n by 3 number of vertices on sides. So if you pick a vertex uniformly at random, then with probability 1 by 3, this guy will not be part of any optimum solution, or at least one optimum solution. So there is an optimum solution which does not contain P with probability at least 1 by 3. Which means there is a two approximate solution which does not contain this P that we picked with probability at least 1 by 3. So assuming there is no large optimum solution, picking any vertex at random will give you a vertex which belongs to a two approximate solution with probability 1 by 3. Right? We will get this guy. So that is what we do. So we look for a two approximate solution S which does not contain this P vertex. Okay. So now if the vertex P that we pick, we assume that it is not part of L. There is a solution which doesn't contain this P. So now if this vertex P is not part of any triangle, so vertex P is not part of any triangle, it is P. If you look at the out neighborhood of P and the in neighborhood of P, there are no edges which go like that. That's why this guy is not part of it. So then we can solve the problem recursively here and there, find two approximate solutions here and there, put them together on the graph. Because this P is not useful in killing any triangle any. So my safety recurs on its in and out name. Right? Okay, the other case P is part of some triangle. So we pick the vertex P, we assume it's not part of the solution, but it's part of a triangle. Right? So now what we know? We have P and it's part of some triangle X. Right? This is not in a solution that you're looking for, which means one of these two guys must be in that solution. So here is a set of size 2, of which at least one must belong to any or the solution that we are looking for. So then we apply the local ratio technique to this pair X1. And we look at the smallest weight of this and reduce that weight from X and Y. So this is a polynomial procedure. So you will repeat this till P doesn't belong to any that, and then you will press on the rest.
So where are you using the fact that there is no optimum solution at that? Oh, the probability.
Yeah. You pick something and so now we put this all together. So if T has the smallest weight, with the vertex set of contain at least 2 and 3 vertices, then we sort of pick this lowest weight guys into a solution because that's the ratio applies sort of globally. And if T has no smallest weight with by vertex set which has too many vertices, then we take sort of guess this vertex, which is guaranteed to be not in a solution, not in a solution, and then do something depending on whether it's part of a triangle or not. So that's the algorithm. There are two cases, and you know what to do in each case. What's the trouble with this? Yeah, how? It's a big if. How do you figure out whether a given input has a solution with at least 2 n by 3? Okay. So that's the third step, right? I mean, which is plain old branching and dividing. Right. So what we do is this. So given the input, so this is now a branching output and dividing output. So if the input is small, we just solve a brute force. And if the input is not small, we first compute a solution S0, assuming that our first assumption was that there is some solution which has at least 2 n by 3. In this case, we know what to do. We do that recursively. And then we also do sort of fun for the other possibility. So for that, what we do is we compute some number of solutions, feedback vertex set. So this part is assuming that there is no large size solution. Yeah. So we pick a vertex P from a random from a particular set. So this is a set of vertices whose out degrees and in degrees are at most 8 by 9. So the set we pick a vertex from among those whose out degrees are at most 8 n by 9. These numbers we need for the correctness and running time. So out degree at most 8 n by 9 and in degree. So we pick a vertex uniformly random from this set, not from the entire graph, like I said, but from this particular set. And then we apply the learning ratio. So this gives us some number of solutions. And from among all these, like 26 solutions, we pick the one of the minimum. Yeah. Each of these is guaranteed to be a feedback vertex. We pick one of the smallest weight from among these. These numbers we'll see why they are important, but this is the general idea. We don't know which are so we try both. And pick the best of them. Okay. So let's look at the running time analysis. So the recurrence is this. In the large step solution, which is when you assume that the S0, when you assume that there is a solution with 8 n by 9 or 2 n by 3 versus. In that step, the recursion is on a graph with, we remove n by 6 vertices. So the recursion is on a graph with 5 n by 6 vertices, which is at most 8 n by 9. In the small step case, there are 25 of those. So what we did was we found a vertex P of this sort and recursion on its in and out neighbor. And we took P from a set whose out degree is at most 8 n by 9 and in degree is at most 8 n by 9. So whenever we recurse on these two sets have size at most 8 n by 9. And we do this 25 times, and each time there are two things. So that gives us 51, 1 plus 50, 2 graph. And this resolves to n to the 35. Master. Okay. Alright, so that is running time is 41. Okay. Now the claim is that when we do this, we actually get.
So that 25 is related to that 18 by 9.
Yeah. It's also related to getting the probability of success to be against up between this. Right. So the claim is that what we did actually, yeah.
So the large resolution size is large, you need an L.
Yeah. So this is the n by 6 version of the smallest weight.
In the whole
In the whole thing. Yeah. We just pick some n by 6 there of the smallest weight. Right. So the claim is that what we did is actually it outputs actually feedback vertex set of weight at twice the best. The proof is by induction on the number of vertices in the program. If the instance is small, we can actually solve it optimally in prolonged time, return on the exact value. Okay. So then we look at the two other cases, like the inductive cases. If this case happens to have an optimum solution which is large, then this S0, yeah, we recurse on a smaller instance. We took all of these small weight guys, plus we recurse on a smaller instance to get an S0. And that as a smaller instance, so by inductive hypothesis, inductive assumption, it is what we get when we work on the smaller instance is a two approximate solution with probability at least half. So we take L and S0, lowest weight guys, plus what we got. And since we work on a smaller weight, smaller size graph to get S0, assume by induction that we can assume that induction that this is true. Alright? Okay, so now in the other case, if the input had no solution with a small number or a large number of vertices, then you compute each of these 25 solutions, the probability that P, the vertex P that we pick, is not in the optimum, is at least 1 by 9. Right? Because if this graph had no optimum solution with like 2n by 3 vertices, delete any solution, optimum solution, you will be left with at least n by 3 vertices. Yeah? If you delete a feedback vertex or small space, you will be left with at least n by 3 vertices. And these n by 3 vertices, they form an acyclic element. So they can be written in this order. Yeah? There is a topological order where every arc is from left to right. Okay? And there are at least n by 3 of these. Now, sort of partition this into first n by 9, second n by 9, and third n by 9. If you look at the middle set, each of them satisfy this condition. Their oblique is at most 8n by 9 because there are n by 9 guys in the integer. And the integer, the entire graph, is at most 8n by 9 because even in the small graph there are already n by 9 guys going. So if you pick the vertex P from among those vertices, since there are at least n by 9 vertices which satisfy that condition, the probability that you pick a good vertex is at least 1 by 9. You pick from a restricted set, but the restricted set is already big enough. It's like at least n by 9. So there are n vertices in total. This set has n by 9 vertices. So if you pick something at random, you pick one from this set with the probability of at least n by 1 by 9. So with so the two recursive solutions, which are on smaller instances, they are good with probability half. So each SI is good with probability 1 by 9 times 1 by 4. Half, 1 by 36. So at least one of the 25 guys that we found is good with probability at least half. So here also 25 counts. Found 25 guys. Each of them is good with probability 1 by 36. So at least one of them is good with probability 1 by 2. So that's what. So there is a randomized polynomial algorithm which will find two approximate solutions for weighted feedback vector with probability at least half. And we can de-randomize this to run in this kind of time by not doing this problem like picking some guy at random to recurse. Instead, try every vertex whose index is at least at most n by 9, it is at most n by 9, 8n by 9. There are like n of those at most. So then we get to the curves and it solves to think order of it. So often problems. First thing is can we get a deterministic algorithm and not n 34 and 2, 3. And then can we try this approach to get two approximation algorithms for other pre-hitting set problems. So this was a problem of hitting a set of size 3 triangles. So one instance, the thing is called cluster vertex deletion. So we run a graph, undirected graph, find a small set of vertices whose deletion we